It's streaming now, and I should also formally put in attendance. So we're working on this page. For anybody just joining us, we started off with a summary of what an atom is, electrons, protons, and neutrons, their symbol and their charges and location and masses in the nucleus, how to read the periodic table, all reviewed from grade 10, and how the periodic table is arranged, how to identify elements as isotopes by their differences in mass numbers, and how to calculate the number of neutrons. It's mass number minus atomic number, which will give you the number of neutrons. And then a practice one with these two particular isotopes. And now we are filling out. I hint that you should never use the atomic mass in this table. It says mass number. So this table does not require your periodic table except to look up the number of protons or the identity based on the number of protons. But you do not need it for mass number. So for example, for chlorine, since I was just asked about that one, chlorine, I give you the number of neutrons is 19. So if you give me something based on the mass, on the atomic mass, it might be incorrect because I'm talking about this isotope. And cool's not here. How many people have done the table? 22. Feel almost done. Okay. How are we doing? There we go. Okay. We'll just go through, fill it in, see what we get. I'll start at the back with Michael. Let's start there. 14 moving forward. 7. All the way back over here. Louder. Oxygen. Moving up. 8. Jumping forward. 0 charge. Electrons and those are the same. Keeping moving along. 27. 32. 7. 0. 27 protons, 27 electrons. It's going to have a 0 charge. Jumping back. 36. 17. And 17 protons, 18 electrons. Michael, what would the charge be? -1. Excellent. Moving back up again. Lithium, number of neutrons. 4. Sorry, louder. 3. 1. So we often put +1, but 1 is also correct. And then moving up. 31. 15. And number of electrons for a -3 charge. 18. Now, what two columns must always be the same? Yeah. So these must always be equal. Any other columns that always have to match? Do the protons and electrons match in every case? No. You could make a relationship with a charge. Based on the charge, how would you get, say, the number of electrons from the charge and the number of protons? You add or subtract. So we need a consistent one. Do we add or subtract? You add. So 15 plus -3 would give us, sorry, I wrote 18 there because I was looking over at the charge. So if I go 15 plus -3, I end up with 12 for my. No, 15 is the already. So that's my. Yeah, if I want to find out the number of electrons and I use charge and I add the charge up, because remember the charge is done by electrons which are negative, so everything would be. So I want to find out the number of electrons from the number of protons. You go number of protons minus the charge should equal the number of electrons. Then you would have 15 minus -3, which is equal to 18, which would get. You can make little formulas for all of these if you'd like. The formulas, if you memorize them and you find, don't really help. Although sometimes that's useful if you're doing a large column like this, if you're doing something like that, to remember how they're related. So this minus the number of protons would give you electrons. Always remembering electrons are negative and protons are positive, so they cancel themselves out. One way that sometimes I find it helps to look at that, this helped me when I was in like grade 10 or something, is that I looked at it like a teeter-totter, and I would have the number of protons on one side and the number of electrons on the other side, because they're supposed to cancel out. And if you had, for example, 17 protons and 17 electrons, then you have a 0 charge. But that's not doing the thing. There we go. if you had 20 electrons, what would be the charge? -3. The negative side is going down by 3. Remembering it's the negative side, it would be -3. And the balance idea that they have to balance out, and then you look by how much they're off, and then look at their charge, I found helpful at times. We've been going a long time on just notes, and we have more Bohr models to do, but let's go in 9:19. We'll begin again. You've got 5 minutes to go grab a drink or refresh your brain scrolling on something. Take 5. I'm going to check my email. Okay, we will come back to our notes for the last 15 minutes of class. I would like you to draw some Bohr models. What we're going to draw is you may have previously drawn Bohr models like this. Say you put the number of protons in the nucleus, the number of electrons. You would draw a little circle around it, and then you would draw another circle, and then you go, oh look, there's an electron there. And you draw them as dots around a circle. That takes a really long time. And you have to count the number of dots. A lot of times that's really annoying. You are allowed to draw them, and you can say, oh, I've got one proton similar to before, but we don't need to draw a whole circle. We know that's the nucleus. And we would just say, oh, there's an electron out here. If we need to, we can say there's one electron. And then we would just start like, this is a whole circle. But do we need to draw the entire circle? We can just probably just say, look, I drew lines above and below so you know that it goes around the circle. But we'll just say that because I did that, you know that circle goes around. And now that is also a Bohr model. Draw both models for helium, lithium, lithium-3, and we have another lithium after that. I want you to draw the most likely ion it's going to have a charge. Gesundheit again. Oh, that's a Lewis dot diagram. That's different. Lewis dot diagrams only consider the valence electrons, which are the only important electrons. They're like, the seniors in the house. You wouldn't count all the juniors. They don't matter.
What is the charge for the last one?
Yes. What? The most likely one. So for the last term, I drew a little pink line. That's for us to write in the most likely charge. What charge should it be? Oh, no, it's not going to be neutral.
But it is exactly the same as here.
Yeah, it's got 3 protons and 4 neutrons, but it's not going to stay that way. Lithium really hates being neutral. As soon as it encounters some water or oxygen, it's going to rapidly become non-neutral. There you go. Yeah. The Bohr model, in much the same way that Newton we know is wrong, and I know that it often feels like we say, this year is all a complete lie. Your future teacher will tell you that what the previous teacher said was wrong, and then you'll learn something else. Have you heard that before in science? Yeah. And there's a reason for that. The reason is it's really hard to explain the most complex model right away. It's helpful to build up for it. And the most complex model is not always the best model. If you were trying to send a rocket to the moon, you only need Newton. Einsteinian corrections will not help you. They will make the math a lot harder, and it doesn't do anything for the accuracy. You're still within the sig figs you need to get the rocket to the moon. And so the Newton model works really well up until Earth orbit. If you're trying to get to Mercury, then you kind of need Einstein, because Mercury moves just fast enough that its orbit is thrown off a little bit by its speed over time, such that you need Einstein to account for its orbit in addition to Newton. Same thing, we're going to do quantum chemistry in the future, which will then tell you that the Bohr model is a lie. But we can do almost all the chemistry we do at the high school level and first couple of years in university without quantum. Bohr model explains everything. We've got electrons in certain orbits. They jump back and forth. When they jump back and forth, they either have to absorb energy or give off energy. And they only exist in certain numbers, 2, 8, 8, 18. Yeah. We're doing quantum this year. Yeah. You'll get some quantum. Yeah. And you'll love it. It's so much fun. It's great. There's one part of it I'll show you. I had a professor at one of the universities. I'm like, what do you want me to teach you chemistry? And he says, do you do quantum? And you go, yeah. Well, teach them this one chart. And I'm like, yeah, we already do that. Well, make them memorize it. And I'm like, yeah, well, we do this and this. I don't care if they understand it. Make sure they memorize this chart. You'll get to see that chart and you'll memorize that. And then you'll have done all the quantum for your university professors. And hopefully you'll even understand it. But if not, he'll be happy at least if you have it memorized. Apparently he was very frustrated with his students that day. Okay. Little Bohr models. You should now for every one of these. I'm just gonna steal these, and then you draw another circle. Now, how many drew their electrons far apart? Yeah, they should be next to each other in the first orbital. They pair up. It's not. You would have been taught that by a previous teacher. Once again, that's a previous thing. But electrons pair up once they run out of different orbitals to go to. And the first level fits how many electrons? 2. So there's only one spot. So they both go in the same spot. They do, yeah. So they get away with that by flipping their spin. Which, I like you said okay. I just said words that I don't think that they flipped their spin. Does that have meaning to you? No, really. If we're filling up, here's the Bohr model. This is where the electrons go. I'm going to make that smaller. I don't know why I made it so big. And let's say that's the first orbital. It could fit 2 electrons. How much can the next orbital fit? 8. So we got 1, 2, 3, 4 spots. And then when we go up again, it's 8 again. And then what is it? 18. 1, 2, 3, 4, 1, 2. It does that. Now, when you fill it up, you would say, oh, here's an electron. And then when we put in the other electron, we go like that. They have this property we call spin. It's not spin, but if you squint at it really hard and you want to call it angular momentum, you could. And so it's like spin. We call it spin. If they put their spins opposite, they'll fit into the orbital better, even though they're the same charge. But when they're spread apart, they go in separately, which is why when we do the Bohr model, you have some number of protons, some number of neutrons. You do the first one. I would do there, but you were probably taught to spread them out. But when you did the next one, I'll bet you did something like this, right? You put them in the 4 corners, and then you start filling them up that way? Or do you spread them evenly? How many of you would do evenly? Sonia? You would? Yeah, no. Because some teachers don't make the distinguish between that, and they're teaching you an easier model. If you learned evenly at some point, especially when you do Lewis diagrams, you learn they go in the 4 quadrants. It's because there is literally 4 spots. And then when we filled up 4, you actually spread them out into 4. So you've got 1, 2, 3, 4. And as soon as you have 5, it joins another one. They start pairing up. That is true in the Bohr model, but this right here, that's the quantum model. So this energy diagram is now joining these 2 models, and now we're going to ignore that. Do the next one. Oh, I really ran out of room here. Oh yeah, I haven't done that, have I? Sorry. So, and then here I go two. I want you to now that you've seen this, I want you to draw it that way and be able to draw that if you need to. Because this is way easier to do. I always write because I read from left to right. On the top? No, if you were Japanese and you did this, I would go, oh, that's a little bit strange, but you grew up reading from right to left. But if you put it on top, you're just insane. Oh, those things. These things here? Yeah, I don't care. Those can go anywhere. But not like that. You put them like that, right? Yeah. Okay, you're not that crazy. Okay, excellent. And then you'd have your circle, and then you'd have another circle, and then you would have your 2, and then your 1. And I'm running out of room. So I'm just going to give myself more room. I'm sure you can do the same thing. Oh, and I forgot to put the new neutrons in here. 2 protons, 2 neutrons, 2 electrons, 1 electron. And the most likely charge for lithium is? Oh, hold it. I just copied what I had above. Thank you. You're the only one who corrected me. 3 protons, 4 neutrons, 2 and 1. There we go. What's the most likely charge? Positive 1. Why? That's where it is in the periodic table is a good practical answer. Why is it there in the periodic table? Yeah.
Because enough, which means that it has 3 electrons, right? But we want to have like the gas configuration of the gases, like helium and neon. So it like tries to like lose 1 electron to gain like satisfied with the number of electrons to be like neutral and not like 1 electron or the other, like orbit.
I like how you said satisfied and you did air quotes because that is so true to everything we're going to talk about now and have been talking about. Have I shown you the treachery of images? I think I've done that. Where is it? Because I'm going to talk about those electrons are satisfied, but I've shown you this picture before, right? No? Oh, okay. What does it say for those of you that speak French? Yeah. Is that a pipe? Is that a pipe? We. No, that's not a, what is that? That's not a pipe. What is it? This is a very famous picture. It's a painting. That's not a pipe, that's a painting. Is that a painting? No. That is a digital reconstruction of a projection of a painting of a pipe. Is that a pipe? You can't, no, it's not a pipe. You can't smoke it. You can't hold it in your hands and have fond memories of your grandfather smoking the pipe before he died of cancer. Like, none of that can happen. That's not a pipe. And the treachery of images fits really well into science because I'm going to tell you things like the electrons, the atom wants to have a configuration like a noble gas. Do atoms want anything? They're not alive. They have no feelings. They don't want. I am substituting words for other words to make it make sense. But never forget, we are using analogies and metaphor, and those things are very strictly speaking not true. Why hold it? I have like 30 seconds. What are you doing? The bell hasn't gone. It is 9:34 and 50 seconds.
talking about
The pipe was amazing. I like bringing that up every time. So, have you heard of you've heard of DNA?
Yeah.
Is it a blueprint?
No.
No. It is not a set of instructions, not a set of computer instructions. It's also not a blueprint. It is a series of codons that undergo chemical reactions, and that is it. Thank you. Pardon? 288. Yep. How many in the third one? And you're gonna really get annoyed by this. It's actually 2818.
Yeah, that's why. Why 18? I thought it's in that octet rule 8.
It is, but that's only because the octet rule was made with things that only went up to 288. So the octet rule works basically for carbon, nitrogen, oxygen, and fluorine, and that's it.
Oh, but why is it not 28818? Because there's in the third column.
Yeah.
There's still only 8 molecules.
Right. So yeah, if you can use the periodic table, it goes 2, 8, 8, and then 18.
Yeah.
18, and then 32 because you add these ones on.
Yeah.
Is it 2818?
It's actually 2818.
No, but why?
Oh, because then we have to do quantum.
I think it's
The other 10
then we have 8, and then we have
that would go into the 18 that doesn't come until later gets filled later, but it actually belongs in the first group.
here. This is the first shell.
Yeah.
This is the second shell. 1, 2, 3, 4, 5, 6,
Yes.
7, 8, 9, 10.
Have you done quantum chemistry?
Yeah, I did.
Yeah. So you've done like 1s2, 2s2? Yeah.
1, 2, and then this belongs in here. So we have 1, 2, 3, 4, 5, 6, 7, 8, plus these all.
There you go.
Thank you.
You're welcome.